It's hard to understand what's happening in the electron transport chain without some sense of physically what's happening to pump H+ hydrogen ions across the mitochondrial membrane. In this video, I'll run through a model by VRI Kayla, published in 2018. This is Electron Transport Complex 1, this thing that looks a bit like a hockey stick, and the membrane is on either side. Inside is the matrix, outside is the intermembrane space between the outer molecular membrane of mitochondria and the inner membrane of mitochondria. There's a binding pocket for Q, quinone. Quinone is one of the electron transporters or electron carriers that transports electrons between complex 1, 3, and 4. It's a carbon ring with a tail, and it fits neatly into this little pocket. So I'm going to call it Q. The complex has 4 ion pump regions. They're hydrogen transport regions, and they come preloaded in 3 of them with a hydrogen now in the middle. NADH binds and gives off 2 electrons, leaving NAD+ and H+. Those 2 electrons jump through iron sulfate complexes, FeS. There's more than 7 or 8 of them, and I'm showing only a few. The electrons jump and they get to the quinone, where 2 electrons are now attached to that quinone, which attracts positive charge from nearby amino acids. Those H+ bind to the quinone, and that movement of positive charge allows the last of the 4 hydrogens to enter. So now all 4 are loaded. First step, NADH binds, move electrons, number 3, and NAD+ and H+ can leave. Add those electrons to quinone. Adding those electrons to quinone allows us to load that final H+. Now there's an important step in which the quinone moves position. It's no longer quinone because it's QH2, and that change in position causes a shift in positive charge that goes across all 4 of the ion transport regions. And in the last one, it pushes an amino acid out of the way that opens up a gate that allows H+ to leave. To run through these again, we have 6, 7, 8, and 9 amino acids have shifted position and positive charges have moved. H+ moving out of the last of those units allows a new H+ to enter, that's in blue, which causes a change in charge that opens up a gate that moves the next one out, and that allows a new H+ to enter. That new H+ causes a shift in charge that opens up a gate that moves the third H+ out, which allows a new H+ to enter for that location, and finally pushes the last H+ out. Remember, we don't reload a new one. That won't happen until the next cycle. So now we've moved 4 H+ out of the complex. So we've pumped 4 hydrogens across. We've reloaded 3 hydrogens. That last hydrogen moving out changes the shape of the binding region for QH2, and QH2 leaves. That loss of QH2 allows a new quinone to enter, and we can start the whole process over again. I've told you about charges moving through complex 1 in order to cause the hydrogens to leave complex 1 and to reload new hydrogens into complex 1. I want to give you more information on how that happens. The electrons that are coming from NADH move through the iron-sulfur complexes to Q, forming first Q with 2 electrons and then QH2. When the QH2 changes positions, that change pushes some positive charge away. There's a whole chain of positively charged amino acids inside the middle of this membrane, and they're a little bit free to move. They can flex back and forth. They're pushed away. Each new positive charge pushes the next positive charge a little bit further away. The positive and negative charges have 2 roles. One is that you need some negative charges to hold the H+ loaded inside the transporting region, inside the middle of the protein. And you also need positive charges because the shift in positive charge from Q will push positive charge all the way down the length of complex 1. At the end, that last movement of positive charge opens up a gate that allows the hydrogen H+ to leave to the intramembrane space. Once it's out, that is one less positive charge in that part of the protein, and there's a space from the other side that opens up that a new H+ can come and reload. That new H+ is now in a position to shift another amino acid in the next segment over and push an H+ out. which allows a new H plus to load there, and so on. The mechanism for causing this change from the electron transport over on the right side to all of the protons moving out at a distance is this chain of movable, positively charged amino acids through the middle of the protein, each one pushing the next one over like a chain of dominoes, along with enough negative charges to hold on to the protons, the H pluses. Now let me take you through it in a fast sketch. Here's the membrane. Complex 1, binding pocket for quinone, there's quinone. 4 H plus transporting regions, 3 are preloaded. There's the quinone, NADH binds, loses NAD plus, NH plus. The iron-sulfur complexes transfer electrons to the quinone, causing it to bring in some hydrogens from nearby amino acids, which causes movement of hydrogen that allows the last H plus to load. QH2 shifts position, and that pushes positive charge all the way down the complex. It opens up a gate that allows the hydrogen to leave. And step by step, we move one out, replace a new one. We move one out, replace a new one, move out the last one, but we don't reload the very last one. We have 4 H pluses into the intermembrane space. And that last change causes QH2 to leave. We reload a new Q.